Um, okay, so ladies and gentlemen, it's getting towards the final component of the day, and I'm sure you have increasing numbers of items on your mind for thinking about outside of the context of this boot camp. And I'm really grateful for your attention, even to this late point in the day. I believe that some of the most exciting material in this boot camp is material you're about to hear. And I hope to reward you for your continued presence and making good use of the time and alerting you to some useful skills when it comes to any logic, and to highlight the potential implications of what I consider one of the more important developments in recent years for dynamic modeling. And I'm going to start with that latter thing. I'm going to be talking here in a very brief way, circumscribed by the time, about this technique known as particle filtering. And particle filtering is a technique that is immediately actionable. We have probably 6 or 7 different models where we've conducted particle filtering, all focused around the health areas. Everything from vector-borne illness to TB to pertussis and measles to biomedical processes associated with HPA axis and stress levels on the part of individuals, to HIV dynamics associated with viral load and CD4 counts. It's a very versatile approach, but it's an approach with strong implications, almost philosophically, for modeling and dynamic modeling and how it's conducted. And regrettably, to hit the approach at a really thorough level is not possible given the time constraints we have here. I have some more material I also consider very important that I do want to hit before the bell tolls 5. But I want to provide a substantive introduction to particle filter, at least at a high level. And the reflection that I'd like to begin with regarding particle filtering is that all these models we've been working with, no matter how rich in terms of the processes in there, they're inevitably abstractions. We have a quite rich model that we've been building up, as you know, associated with smoking. And we could marvel at the number of different factors that are included in this model, spanning from aspects of heart disease to aspects of smoking, etc. But inevitably, as I've tried to make the point, that's a simplification of the world. And in fact, it's this capacity to omit details that makes models and maps feasible and useful. And I've argued in an earlier lecture that models, like maps, are specific to purpose. And yet it's hard often ahead of time to know what features are essential to capture within models. Simulation models, as I noted, have many purposes. And one of the big purposes to which we put them is to anticipate and plan around trends. And equally, or even more importantly, to ask what-if questions, to identify interventions that are likely to be high leverage. Now, the challenge that faces me as a practical modeler, working with groups in Public Health Agency of Canada or various ministries of health or health regions and their amalgamations within the Canadian context, is that we're often working with emerging infections or emerging situations where we don't have tremendous bodies of evidence to draw on. We have evidence here and there, but there's substantial portions that we'd like to use to inform our model where evidence may be lacking, it may be dated, it may be compromised by quality issues, etc. And there are times when especially when we think about emerging issues, the SARS, the MERS, the H1N1, et cetera, of the world, that by the time a highly grounded model can be created based on very careful studies, observations, often the greatest chance to shape policy is past. The greatest urgency of the moment has now passed us by. So that's one reflection. That often we're stuck in this catch-22 where we'd like to build a model quickly to address an urgent policy issue, but where that model can't be nearly as grounded as we'd like because the data, the understanding isn't available yet. The second reflection I'd like to make is that, look, even the most detailed model, if we build it now, most exquisitely calibrated, parameterized model, where we've collected large amounts of empirical data ourselves in primary data collection studies, we've engaged in secondary data reuse, we've tapped big databases of information from administrative data to our smartphone-based collection systems. Inevitably, these models eventually diverge from empirical worlds. I mean, even the most accurate depiction of the situation now may involve a lot of stochastics, and we don't know going forward which way those stochastics will turn out. They'll turn out some particular way, and we don't know now. We don't have the knowledge of which way it will turn out, and the world will evolve off that trajectory that we can't fully anticipate right now. But more realistically, a lot of the times our models omit factors that could be relevant. There are approximations within those models. There's new influences that come in. There's latent heterogeneity in terms of the model that we don't have well broken out, and misunderstandings regarding the character of the process. Thirdly, and based on that first observation, in many situations to address planning needs, we either face a situation of planning based on a very inaccurate model or an incomplete model that grows increasingly disconnected from the actual situation, or a highly detailed model that isn't available in time. So that's part of the quandary I face as a modeler, and I put it in especially stark terms. I actually still think we can deliver a lot of value for our thinking there, making better decisions. But in stark terms, a lot of the issues are we build beautiful models and they come too late for the most urgent policy needs, or we have a model that we put so much love and care into and it grows outdated over time. And it takes a lot of work to recalibrate it, et cetera. So the motivating solution here reflects on the fact that calibration, really grounding a model right now, is a very highly manual process that involves a lot of efforts. But we have ways of dealing with daily living that clue us into a better approach. So the reflection here is that, look, when it comes to our mental models, which Jeff and Eric argued the position, and I very much buy into this. It's a common one in system dynamics literature, that we always make decisions based on models. The question is what sort of models we're making decisions on. Is it the models in our head, the models in wetware, the models are obscure to others that we can't really critique, that aren't thought through, can't be precisely, the implications can't be precisely derived in an automated way? Or is it a model that's explicit, that says the full light of day, that multiple people can look at, critique, advance, refine, etc.? When we're dealing with our mental models, though, we have a real asset that we use, that we tap into, and that's ongoing observation. We observe new data as it comes in, and we use it to update our mental model. Were it only that our computational models, our models that we build in tools like AnyLogic, could be similarly agile in the sense of getting new inputs, new observations, and nimbly sort of taking those into account in our planning. That's one benefit that our mental models have. And the analogy I gave the other day, just to motivate this work, is when we head home from this event, to our hotels, to the airport, or to our homes. The fact is that we do so not just with a perhaps very refined mental model of how to get home from here, but we do so in the midst of a constant process of observing our situation. We constantly get new understanding about where we're at. So even if we know by heart every single stop on that bus to our home, every single turn in the street and on the sidewalk to get home, to try to do so without observing along the way would be a fit of madness. It would be a fool's errand. We'd end up in a very bad way because of stochastics of traffic. We can't interpret, and we can't anticipate which way the light will be at a certain time. And very importantly, growing in accuracy. And I emphasize growing in accuracy in our sense of where we are at a given time. If we were to try to traipse out with our eyes shut, board a bus, etc., we grow increasingly disconnected with where are we until we could grasp onto something that we could sense or see. And the observation here is that our mental model is absolutely critical how to get home. I mean, without that, we'd be in dire straits. We couldn't get home either. But our observations are also needed, our observations along the way. They clue us into where we are in a way that really enhances our strengths. And so the question here is, why do we base planning and projections on blind simulation models? On models that aren't regrounded with the latest observations to clue them into what the current situation is so we can always look forward more reliably. Just as we go home, we look up, we find out where we are, and we end up able to much better navigate the next few steps. So, here I'd argued at this event that dynamic models help us make sense of data, and data can help ground those models. That's one of the most sort of fundamental of connections. And the vision that motivated this work is one of quickly formulated and frequently regrounded dynamic models. It's models that can be pulled together very quickly in a way that accommodates the limitations of data, that accommodates the limitations of understanding, and that benefit in the same way we do on our way home from ongoing observation, that improve the understanding about what the current situation is, and thereby what we can expect in the next little bit, or how the situation will be different if we make this choice versus the other choice. Okay, so here we're trying to learn from observation all through the time with the model. And the model is kept current with the latest evidence. And we can use that to project forward and study intervention trade-offs. It's hard to assess interventions and their impact if we don't know the current situation decently well. It's hard to say, how would this intervention affect things? I mean, if we're talking about an outbreak response and immunization campaign, unless we have some sense of how many kids out there of the targeted group are susceptible, it's going to be hard to know how much of a difference that will make. After all, a great fraction are already immunized. We're going to have a lot less impact than we think. We might put a lot of effort into something that yields very little gains. So one way to accomplish this automatic regrounding is through the technique I'm going to be showing you. It's called particle filtering. Okay, and it's a technique that has hit the world by storm in other areas of work, including robotics and some aspects of dynamic machine learning. Its application in health has been very, very, very limited. I'm aware of fewer than 10 contributions, many of them from my lab in this area. So in the highest level terms, and I'm going to keep this presentation at a very high level because of the limitations in time and the diversity of audience understanding. At a very highest level terms, particle filtering balances between confidence in a model's predictions on the one hand, recognizing that model's predictions are fallible, and data, recognizing that data is noisy and fallible as well. We have observations, but those observations are incomplete, often biased, and we have model predictions, but those predictions are based on what may be flawed depictions of a situation, which are inevitably flawed depictions. They may be very useful, but they're often somewhat inaccurate in certain regards. So the particle filter is going to help us balance these two and form a consensus estimate. In fact, in the form of a distribution from which we sample, associated with what the current situation is, the latent state of that model, the state of the model that's currently arriving. And this is going to consider ongoing incoming data that's coming in over time, and model predictions. But it's going to do so in a way that doesn't require that huge effort we talked about earlier with model calibration. An effort rewarded by learning and very valuable. But here, we're actually taking into account each new data point over time in a substantive way. And it's, through particle filtering, telling us what the implications are in terms of our understanding about what the hidden underlying state of the system is right now. Okay. So this particle filter is going to allow us to sample from, that is to draw potential, to articulate a distribution over, a non-parametric distribution over the model state, the current, how many people are there in these different categories, for example. And it's going to allow us to take that into account in projecting the impact of interventions going forward. It will also provide us some way of understanding how parameters might be changing over time. Okay? So this is going to be able to provide a distribution over, a distribution that is informed by this data that's coming in over trajectories that we can expect going forward and outcomes. Okay? So we'll have something like this. This is some of our earliest work here, but it shows the basic feature. And I apologize for the crude nature of this, but what I've showed you here is a deliberately poor model. A model is parameterized way off. It's way off in its depiction. And over time, it expects a growing number of individuals here to be infected. And you can see, as a data item comes in, it gets fairly confident about the current situation. But the longer it goes between an observation, it gets wilder and wilder ideas about how many people are infected. And it gets more and more uncertain about how many people are there. Well, it could be small, it could be large. New data comes in, it regrounds it. It updates its estimate of what the current situation is. Much as if I started walking around and then, after 5 minutes I looked, I said, oh man, I'm there. Oh, okay, now I'll head this way. I've become very confident, but the longer it goes without looking, without peeking, the more and more uncertain I'd be about where I am, without having some basis for knowing where I am. But with enough peeking, with enough kind of looking out, I can sort of anticipate where I am at any one point that's not too horribly off, because I'm constantly being brought back to where I am. And over short periods of time, my expectations, my anticipation of what's likely is going to be off, but it's not going to be off in a huge way. Now, our earliest work along these lines used a technique known as Kalman filtering that was articulated in the 1950s, okay, and has a central role in guiding today's aerospace applications as well as others. This is a very well-defined principle rule or technique that allows us to have data coming in potentially many times a second, even hundreds of times a second, and take that data into account. Now, if you are dealing with a rocket or a plane, and you are getting data many times a second or times a minute, this is a great technique. It allows you to very quickly update your estimates in the model. But it has very, very stiff assumptions with it. And I'm not going to go into these, but they have to do with the nature of the inaccuracies that assumes they're all Gaussian distributed, that the measurements are Gaussian distributed as well, that they have a normal distribution of the errors. And these estimates, while perhaps not bad if you're flying a plane or something, if you're dealing with small counts of TB cases, assuming that the errors are normally distributed is a big problem. You're dealing with 1 to 5 cases, and you're saying it's a normally distributed error. It's just not gonna cut it. By contrast, the particle filtering approach that we're talking about it requires more computational effort, But frankly, in health, we don't need, if only we were dealing with data, coming in multiple times a second about our healthcare system. We're not, and we have the luxury of taking minutes to incorporate each new data point about how many people there are in the ED for the emergency department, or the number of people that have gotten sick in the last day. If it takes a few minutes to take that into account, it's not a big deal. It has very flexible distributional assumptions, specifying a general likelihood function, and it doesn't assume a special form, as does Kalman filtering, about the model. Kalman filtering assumes that it's a nice mathematical model and differential equations that we can differentiate and linearize in a nice way. And this is not something particle filtering requires. Just to give you a flavor of this, I'll give two little glimpses of case studies. These are practical cases with real data and real models built by students in my lab. These models are very simple, okay? We're starting simple. We have one student, Kirk Kruger, who's applied this to agent-based models. But the problem is it's much easier to do right now in any logic with stock and flow models, okay? It's just the reality of the situation, and I can share a bunch of them with you if you're interested. So here we have a classic type of model we see in infectious disease epi a lot. A number of people susceptible, exposed, infected, recovered, and then some number that are vaccinated, with the idea being that this is a recently vaccinated stock and people go over to the recovered state after, essentially they're immune after a certain amount of time, okay? Little depiction here of H1N1. And we have some estimates here associated with latent times of the sort that can be in time to recovery that might be gained from studies of natural history of infection. So the idea here is that we have data coming in, hence the red data points, and we have model trying to predict forward how many cases there might be. And as new data comes in, it's incorporating that and it's understanding the current situation. How many people are likely in each of these compartments right now? How many people here? How many people here? How many people here? But it's actually got a distribution over its hypotheses about these. So certain hypotheses are much more favorable in terms of how they match the data, and they tend to be favored accordingly in terms of giving them a high level of confidence. Others that fly in the face of the data, one that says there are tons and tons of susceptible people and quite a few infectives, and we're not seeing the cases, tend to be favored less. So, here, a model which would say there's tons and tons of hidden cases out there would not be too consistent with the evidence. But as time goes on, each new data point is received. This is daily data from Manitoba during the H1N1 epidemic. And you can see the model's expectations for what's coming up evolve. It's evolving its sense of how many people there are in each of those states. That's a big thing. But it's also evolving its sense of some additional factors involving contacts between people and involving the likelihood a given person who is infected will in fact be reported to the healthcare system, because that, of course, is important. And that might vary in the course of a perceived pandemic. Early on, people might be inclined to be a bit skeptical. Over time, as some of their people around them and their social networks have gotten struck down, brought into the hospital, even though they're people in their 20s and 30s, they might seek to bring their child in if they're showing symptoms. So we were looking at cases where we were looking at this data and considered possible evolutions in those factors. And you can see as new data comes in, it gets more savvy. It's not perfect. You notice it didn't get quite that downturn here. But as new data comes in, this is prediction after this point. So this data up to this red line has been received, and after there it's predicting forward. And the key point is, it's predicting forward on the basis of a distribution. It's not putting all its eggs in one basket. This is the way forward, as calibration would do, right? Calibration would find one set of parameter values and put its emphasis on that. That is the best match to the data right now. Here, it's actually got a a distribution of hypotheses over what's going on, how many people are in each state, most of which are latent. That is, we can't, for most of these, we don't have the luxury of knowing how many people are here or knowing how many people are really infected. What we know is how many were reported as infected. And this has got, each of these particles has some hypothesis about that, and we're sampling from it, and we're sampling, and we're then looking forward with these samples based on what's currently the case. How might it change over the next little bit? Updating our sense of where we're currently at. Now, if we had run this model, and unfortunately I don't have a graph, if we had run this model from the get-go, way back here, it would have been horribly off. It would have been horribly off. I mean, it would have anticipated, an outbreak that's probably considerably larger than it was. But it's because this data is coming in, the model is being constantly regrounded, it's learning, as it were, from what's been observed, regrounding its current state of where I'm at, just like peeking out, where am I in this, my way home, and using that to look forward with more confidence, but it's also learning something about these parameter values that are changing. What fraction of people are probably reporting their illnesses, or what's this contact rate? How is it likely evolving? And in a fast-changing world where people's behavior does change, these are important things. So this was Manitoba. We also have done this for a bunch of other conditions. Again, TB, H1N1, yes, but we've also done it for aspects of HIV. We've done it for pertussis as well. So here's a situation where we have data over time. This is over months. Each data point is a month. And we have data for several decades from public health reports in our province. And here it's actually using each of these data points to estimate the current state of things, and you'll actually see this distribution of how many people it thinks are infective out there at a given time. And you can see it's a distribution. This is with no predictions. In other words, it's used all the data, and it's just trying to keep according with the observations as to how many people are infected. But I want to highlight the fact, this is the empirical data with the little red dots. I don't know that you can see it that well. And this is the distribution here. But what's implied behind this is it's also got hypotheses about what's going on in terms of the latent factors that we can't easily observe. How many people, for example, are susceptible behind the scenes? How many people are exposed? How many people are recovered? And how many contacts there are per day and the fraction of reported incidents. You notice early on, it was quite uncertain about what fraction of people were being reported. But eventually it comes down to a quite clear confidence that, okay, there's a certain fraction being recorded over time, or being reported over time. Same thing with the number of recovered cases. These are not easy quantities to observe, in contrast to this, where we can observe something about the number of measles cases. Now let's look forward how this model takes into account data to look forward. So we imagine here a situation where we only have subsets of that data. We're going to be looking at cases where we only have the data partway through this series and asking, what does the model think is going to happen going forward? Imagine yourself, you're in the middle of a measles outbreak, and day by day you've got data coming in, you're 4 days into the outbreak, and you want to know what's likely to be the next prognosis of the next few months. This is the sort of question we have people from our health region bringing to us. Remember during the H1N1 epidemic, they said, well, look, this is what it's done so far. It's gone up and then it started to come down. But in some other cities we've heard of, it's had a double peak. Is that likely to happen? Should we really be putting our emphasis into surge capacity, for example, to handle more cases? Or are we past the worst of it? We need to know because we need to plan allocation of resources. Very practical question. So imagine this situation where you've got data to this point, to time, it's about time 30 here, and now you don't know what's going to happen going forward. So even though there's dots here, those dots are just for you. The model is not taking those into account. It doesn't know about those in its projections.
It's only got the data to here. And it's in the middle of a big outbreak here, right at that time, right? It's right in the middle of an outbreak. What does it think is likely to go on after this time? Well, you have to understand, the model's got a hypothesis for what's in each of those underlying stocks that capture its state. And what it thinks is going to happen is it knows, okay, we're in the middle of an outbreak. Because of that, we're draining the number of susceptibles. So in terms of what's likely to happen, it's probably going to fall quite significantly here during this time. And that's going to allow susceptible to go up, and then that's going to allow it to sort of to actually be able to rise again, et cetera. So this is kind of different data points. It can't predict the exact timing of these, which are actually fairly stochastic. But it's got a pretty good understanding of kind of the levels, and for the next few years, it's got a sense that, okay, it's going to be coming down. And you see actually it's imperfect about this. It hasn't anticipated it quite right. It actually stays somewhat higher, but it then does decline from this peak that you see up there over this rough time frame. And once again, you do see a crest here, and then it's at somewhat lower levels consistent with this. Here, it's also anticipating all these other stocks going forward. Let's consider this as time goes on. So here's time 35. So we've got to about this point here, time 35. And after that, so this point here, it's trying to predict what's likely to happen. And you can see it's pretty good at predicting kind of a band of uncertainty here. There are some peaks it misses. This is on the upper end of it. But it's got a pretty good match to the envelope within most data points fall here. And this is the uncertainty it's got in terms of the values of recovered. But the most important thing is, okay, given that we've had data there, what does it think is likely to occur in the next year or two? And once again, it's pretty well on the money here. It's got a sense of, okay, what is the likely distribution of cases in the next year before things start to get really uncertain what's going to go on. It's got a pretty good match to that range of data. Let's continue to take a look at this. Time 44, so we've got it to about here, right? Just about this point. What does it think is likely to occur? It thinks there's going to be kind of a rise here, and then sort of a decline for the next few years in this general area. And once again, it's pretty good in its expectations. It's somewhat overestimating. Now here's an interesting case. Here, it's been in a situation where about time 58, so just before time 60 here, we've been in a situation where it's been a very low rate of infection for the past few years. And you have to understand, it's got hypotheses for what's going on in the underlying system, and has been treating those, lending more confidence to those that are consistent with the data. And what's been consistent with the data are hypotheses where it posits a growing number of susceptibles, okay? Because we've had such low numbers of cases, all the models, all the hypotheses which involve a low number of cases here have posited a situation where, because there's been a low number of cases, the number of susceptibles is going up. So it's anticipating here, by this point, we have a large number of susceptibles. And as a result, going forward, it's predicting quite a few cases in the next few years as probable. Doesn't mean they're definitely going to occur, but as probable. So one of our partners, Alberta Health Services, was seeking to use models to try to attach a probability for the likelihood we'll see an outbreak in the next year, for example. And this is exactly what this is designed to do. Saying, taking into account all the data here, the fact that what does that data imply about the latent variables, now look forward. And this actually got it right on the money in terms of these coming data points. They were right within its envelope. It was expecting that the number of cases is quite possibly high within the next year or two, and it got it exactly right. It's because it knew the number of latent, to explain this data, to be consistent with this data, all the hypotheses point to a higher number of susceptibles building up, which means a high likelihood of an outbreak soon.
Can I just ask,
Yeah.
when you
Yeah.
say hypotheses, do you mean
Particles.
parameter values in the model?
I'll talk about this, okay? I'm trying to give an intuition, and then we'll talk about how it captures it. The way it captures it is what is called particles, and each particle, basically, it's in a concept derived from importance sampling. Each of the particles has a complete hypothesis in the sense of a vector of values for each of the state variables: susceptible, infective, exposed, recovered, vaccinated, plus each of those varying parameters. And each of these particles, and there may be 10,000 of these particles operating at once, it further has a weight associated with essentially how consistent it has been with the data to this point. How much confidence we lend to this in terms of consistency with the data. And at the same time, the model is running with, therefore, 10,000 hypotheses for what might be going on, with the ones that are competitive, that explain the data well, being lent high confidence. And as a result, it tends to favor those in terms of sampling from the distribution, and those tend to be well represented in the distribution. So here, predicting forward from time 75, that's about here, it again captures the fact it's going to decline. There could be a subsequent sort of upsurge. It thinks there's a high chance it could be larger, but there's also a high chance here. It includes this envelope, and it sort of anticipates going forward a sort of broad envelope like that. But what's notable is, again, the next few years, it's capturing pretty well. It's a bit understating how long this outbreak tends to last there. And then from time 75. Okay. So did I? Okay. Oh, I see. This is with different. This is with different technical parameters for the random walk. This is with one that it posits more behavior change, and here it's right on the money. That if behavior can change significantly, it gets that exactly. It nails this peak and then the subsequent decline. This is a representation of how quickly we posit behavior is changing. Here less, here we posit as being able to change fairly quickly, and thereby explaining some of those patterns in terms of predicted from time 90, and this is with a lower behavior change parameter. So I'm gonna this is another example of the types of distributions that come out with respect to other, some of those dogs. For example, force of infection or fraction of reported incidents that's reported or vaccinated. This was actually for an earlier version of the H1N1 model. So how does particle filtering work? Well, basically here the simulation model includes some sort of stochastic processes involving variability that might occur in, for example, infection rates, in contact patterns, etc. Contact rates, fraction of reported incidents. It's got some variability associated with it, incorporated in it. Particle filtering is performed in what we call a recursive fashion. So it actually, the values going forward that it anticipates are based on earlier values that it anticipated based on yet earlier values. And it samples from the distribution of trajectories. What I mean from that is it draws from these what I call hypotheses informally as to how many people are in this, a value here, etc. And it's a joint probability distribution. So, it recognizes that, okay, if this one is high, it means this one is low, or what have you. So each sample is associated with what's called a particle, okay? And the particles at any one time represent a sort of sampling from the state of the model. But some of them have higher weights, indicating they're more, from an importance sampling perspective, they're more represented, more highly represented. And we can compute statistics on the drawn particles to approximate such statistics to the full distribution. So each particle is associated with a complete copy of model state. This is what I commented as sort of a hypothesis about model state. So each particle says, this particle might say, I think there's a high number of susceptibles, a modest number of, 100 exposed, say for Winnipeg, I think there's 600,000 susceptibles, 500 exposed individuals, likely 600 actual infectives, even though I've only heard reported 200 of them, and this many people vaccinated and this many people who are recovered, and there's this contact rate going on and this level of reporting going on. So each particle is associated with a hypothesis about model state, is how I term it. It's got its own idea of what's going on right now in this model. It's also associated with a weight, and that weight basically represents the credibility we've lent to this particle, and I'll describe how that's calculated. It's key. And it's a weight in the same sense in important sampling. We associate each sample from a proposal distribution with a weight. The overall idea behind particle filtering, if you don't want to go into the mathematics, is that there's a survival of the fittest of these particles. A survival of the fittest in the sense that the ones that are more consistent with the data survive, flourish, are replicated, and the ones that are not so consistent with the data, that is those with low weights, the ones that are consistent with it with high weights, and that will allow them to sort of to be reproduced through resampling. And those with low weights are often going to die out. They're not consistent with the data. They have low credibility, and they're likely to disappear at some point. They're just not competitive hypotheses. Okay. And the point is, the trajectories that are more consistent with each new data point survive and are shaped by each new data point in a way that represents this distribution. And typically, there's a fixed number of particles rotating through the simulation. So through this simulation, we have a fixed number of particles. So here's this particle for H1N1, right? And here, we have contact rates and error, and as a result, and we have force of infection. We assume random mixing, no networks here. This is a high-level aggregate model. And that's going to lead the model to have some error. Okay, so the way this is working is between observations, the model just runs normally. But every particle runs normally. It's just running the natural equations of that model, which includes some stochastics, but it's just running forward. We don't do anything fancy. But there's 10,000 of these particles running forward with these different hypotheses between observations. When a new observation comes in, per an approach that goes back many decades and has been used extensively within robotics in terms of particle filtering, what happens is that particle weights are updated at that observation point to reflect the likelihood of observing the empirical data, given the hypothesis, I call it informally, given that particle's thinking of how many people are currently susceptible, exposed, infected, recovered, vaccinated, and its hypothesis about its posited number of people, the contact rate and fraction of cases that get reported. We then say, okay, given that mental model of the world, that hypothesis about the world, what is the likelihood of observing the empirical data given that? So maybe this is a particle over here, exhibit A, we have a particle that posits lots and lots of infectives right now and a pretty significant number of susceptibles still. So maybe 2,000 infectives right now and half the population susceptible. In that case, and I can fill in the other values because it has to have particular assumptions about the other values. And we could ask, what's the likelihood, given that assumption, we'd only have observed 10 cases this week, or this day, as we're operating with H1N1. And the chance there is very small. I mean, possible statistically that just by the luck of the draw, no one's going in to seek care for H1N1 infection. It's possible they're not going in, but it's very implausible. So the likelihood of that would be low. On the other hand, there might be another particle that posits low number of susceptibles and a modest number of infectives, maybe in the 100, and a low number of susceptibles. Now that's more consistent with the empirical data. So its weight will be updated in a way that will tend to grow its weight. There may be another one which posits lots and lots of susceptibles, but very few infectives, just 2 or 3. That's also fairly plausible, so its weight would also be boosted. So you've got these particles with these different theories of the world, the different hypotheses about the current situation going forward, and their weights are increased if they're consistent through the likelihood function with the empirical data, and they grow smaller if they're inconsistent, if the likelihood is too small. And it turns out there's too much disparity in the weights. There's a resampling process that goes on that matches what is done in importance sampling. So it's worth noting that between observations, these particles just run forward. But I told you that a particle might be duplicated in resampling. So in resampling process, if too much disparity is in weights, particles are resampled. And what that means is a given particle that has a high weight might be copied several times, maybe 10 times. This particle with a really high weight gets copied. But it's going to diverge from its siblings because of monostochastics, okay? And this is going to mean that it tends to end up differing from other particles, okay? So at observations, the model estimates of state are corrected by the empirical data in the sense that the weights for particles that are less consistent with that data get smaller, and those that are more consistent get larger. And as a result, when we sample from the distribution of particles according to weight, we're sampling more of the ones that are consistent with that data than we would have before this observation, okay? So each observation is shaping the set of particles in a way that it has survival of the fittest. It's preferring those particles that are consistent with it, okay? So the strategy here is one of important sampling where we're sampling from particular weights. And there's some theory here which I'll provide on the slides there, and I could also refer you to many of our papers on this. So when each new data point comes in, each new observation or set of observations, vector of observations, we update the weights associated with each particle to reflect how well the particle matches the empirical data. And the strategy that we're using is one that dates back to 1998 with Isard and Blake. And it's a strategy called the condensation algorithm. And it's extremely simple. You take the existing weight of that particle and you multiply it by the likelihood of observing the observed data given that particle's vector of values for the different state variables. So the particle thinks there's a certain number of susceptibles, a certain number of exposed, a certain number of infectives, a certain number of recovereds, a certain number of vaccinated, a certain rate of contact, a certain fraction that are getting reported. And we calculate the likelihood function of given that, what's the likelihood of observing the empirical data, and then we have that value, maybe it's 0.002, and we multiply that by our weight to get the updated weight in light of this observation. This technique can work extremely well under certain contexts, and from our experience, it works very well with the examples that we've seen. There's more sophisticated versions that are used in robotics, where you've got different issues having to do with the relative frequency of updates versus how uncertain things get, the rate at which things get uncertain. But this is the basic algorithm here, okay? Isard and Blake, and it's very simple to implement. You just multiply it by the likelihood. So the likelihood function gives the likelihood of observing the empirical data given the model state associated with that particle. So it's for a certain particle, what's the likelihood of observing that data? And given that value, update the weight of that particle by multiplying it by that likelihood. Okay? So if this particle has a state which is very inconsistent with the observation, with this observation y, it's going to have a really small value of the likelihood function. You multiply it by its current weight, that weight is going to get really small. On the other hand, if this particle is positing something that's very consistent with the data, its weight is going to be multiplied by a likelihood that's much, much bigger than that other one. And as a result, its weight is likely to survive at a much higher level. And as a result, when we sample for particles, we're sampling according to weights. And so the ones that have high weights will be well represented. We'll give a lot of credence to those in our understanding of what's going on. Glad this is being caught on video. The screen capture doesn't quite catch it. So we have likelihood functions, ladies and gentlemen, which are based on, and this is based on work by Dora Gotti, wonderful author who shared with us some of her early MCMC work, for which we're really grateful. In 2011, they had a great paper on applications of MCMC for H1N1 in Europe. MCMC rather than particle filtering. But they made use of a negative binomial distribution, which we found really, really handy to link the number we expect to be reported versus the actual reported. And there's a reason we use negative binomial. That's a very practical reason. We're working towards more sophisticated strategies. But basically, a negative binomial has a dispersion parameter associated with it. And as you change the dispersion parameter, you can keep the mean the same. The mean here, I think, is going to be 1,000 every time. But as it increases the dispersion parameter, what this is saying is that we're preferring a likelihood that's more and more unforgiving if it's off. In other words, if it's really wide here, we'll say, oh, if you got a value that's 2,000 and our mean expected value is 1,000, it's not that bad. But if we have a dispersion parameter that's really large, say 64, value 2,000, you're out of the running. I mean, there's just no possibility that this is consistent with our expectations. So the dispersion parameter is something that you end up needing to specify for the likelihood function. And it turns out there's an additional step called the resampling step. This is based on a notion of importance sampling, where basically at some point, if there's too big a divergence or too large a variability in weights, we end up resampling so that the particles that have low weight almost always die out entirely. They were already little sampled because they had low weights, but now they disappear, and the ones with high weights multiply, but then they start diverging going forward. Now, the advantage here is when we sample from these particles right now, we can use it to then sample from future expectations. So we can get a distribution of future expectations over the next month, the next year. But more than that, we can get a distribution over comparisons between intervention A and intervention B. In each case, take into account that we've got some uncertainty about really what's going on right now, but that uncertainty can be reflected by having not just one calibrated set of values to put all our emphasis into, but this distribution of possible outcomes. Okay. Now, we did some work, and I won't go into this because time is too tight. We did a lot of early work to evaluate particle filtering and its efficacy using a strategy that, well, if we wanted to evaluate how accurate it is, there's basically two strategies we used. And I have a comment on there here somewhere. One is to evaluate using the data only to the certain point, like we saw earlier. Only the data till now, partway through all the data we have, how well does it predict forward from that? What's going to happen? We know what's going to happen because we have that extra data, but we use that to test the model, to test the particle filter rather than feeding it into it. So we only take into account the data till partway through, we predict forward, and then we use that to test how well is it doing in terms of its predictions. The first approach we used was actually a ground truth approach, where we actually took a model like this one. We took a model like, and forgive me for going back here, we took a model like this one, an aggregate model, a model with simple assumptions about random mixing, simple contact rate assumptions, and we tested it with particle filtering that was based on a situation where we knew the full situation. That's not possible in the real world. We don't know the full situation, how many people are really infected or exposed. Instead, we fed this data generated by a more complicated agent-based model, which had susceptible, exposed, infected, recovered, and vaccinated individuals, but different values for contact rates, for example, than we originally started with. And it had network structure instead of random mixing, et cetera. And in that one, we found actually it did great in reducing the errors that would have been obtained if we had just gone with the original model. So here we used agent-based model to provide sort of synthetic ground truth to test it, where we drove it with synthetic data and we compared its expectations against what we actually knew was going on in the agent-based model. Okay, that's one strategy. The other strategy was the strategy of predicting forward. So we talked earlier today about calibration. Calibration is a very powerful technique for estimating parameter values. How does it differ from this? Ladies and gentlemen, it can be hard to get your mind around it at a basic level. Both at some level take data, emergent data, and try to improve the model based on that. But the differences are profound, because calibration basically adjusts parameters in this model, to taking out this data. But it doesn't update in any way the model's understanding of what the current situation is, how many people are in each stock, for example. All it does is update the parameters of that model, but it doesn't take into account, this is where I am right now. I must be in a situation with few susceptibles, or a growing number of susceptibles, because I haven't seen many recent cases. The number of susceptibles must be growing. It doesn't take that into account. And as a result, calibration is a great thing, but if you depend on calibration to anticipate what you're going to have going forward, this is the comparison. You'll notice these are discrepancy numbers based on mean squared discrepancy type metric, square root of mean squared discrepancy metric versus with particle filtering. You can see there's orders of magnitude difference here. 800,000 over 800,000 versus just over 1,000. So like, 8,000 times 39,000 versus 554. You're talking a situation where particle filtering can be just vastly more accurate because it's taking into account each new observation, not just to estimate parameter values, but to estimate what's going on right now, how many people are likely in each state, so that we can look forward more surely. It's just like opening your eyes after you've been walking for 5 minutes without them and realizing, okay, that's where I am. Now I have to head this way, or now I have to head that way. You're much more confident in the next few minutes about where you are than you were before you ever got a chance to open your eyes. It's like glimpsing, you're lost in a car, and then you say, oh my God, that's where I am. I know where that is. Okay, now I'll go that way. So this is not a magic technique. It has its limitations. There can be too few particles. There can be what's called particle impoverishments, where there's not enough disparity in particles. We haven't actually had too much problem with either of these. We run it with 1,000 to 10,000 particles. It does fine. And these things run, they run and I think with something like 5,000 particles, maybe you can run this particle filtering about half an hour or something like that with your model. Condensation algorithm, we also haven't had too much problem like that. So a couple points of learning. Particle filtering is powerful in general. It does require some learning and sort of experimenting with it, tuning parameter values, etc., so that it matches really well if it's applied to historic data, predicting forward more historic data. And then once we've gotten those sort of meta parameters, the hyperparameters associated with the distribution, then we could use it going forward with much, much greater confidence. These meta parameters are things like how quickly does human behavior likely change within the context of this population, or how quickly do people change care-seeking behavior, that sort of thing. It's often far more effective than calibration because we're regrounding this latent state, this state of how many people are currently in each state right now. Particle filtering needs to balance having too little confidence, and this is a matter of its parameters, too little confidence about its expectations. It just, after an observation, it gets more and more uncertain. I don't know what's going on. I don't know where I am. It gets more and more uncertain. It needs to balance that tendency with the tendency of having too much confidence. I know exactly where I am, and then being broadsided, or when a new data point comes in, not giving it enough credence. And this tends to give poor biased results. It just persists, in its own sort of benighted way. I call this the Trump approach. So it needs to balance those two. Okay, it needs to balance those two. Having too little confidence, saying I give up. It's just things are so uncertain. I don't know what's going on. And quickly after each data point, just having no clue, versus where it's really overly confident and it's in a way that's just totally off. In outer space. They're going to build the wall. They're going to pay for the wall, and we're going to invade them because they have the bad hombres in Mexico. The inauguration crowd was biggest ever. Tuning probabilistic model parameters makes a big difference for the accuracy of the particle filter. It makes a big difference in how accurate it is. And if the posterior is too diffuse, often particle filter will not help. Actually, this should say if the likelihood function, not posterior. If the likelihood function is too diffuse, which does mean, yes, the posterior by implication. Basically what happens is if your likelihood function is too wide, particle filtering is not going to be able to take advantage of each new data point to narrow its expectations. Okay, so those are some points of learning. There's a lot of mathematics behind this. If people are interested more, I can give you some references. It's well-trodden material from machine learning. And really what we're doing is bringing it to the health side with stock algorithms, well-tried frameworks that have been used in robotics and so on, and using it for health to inform confidence about things, about what can we expect in the next few months, or how is this decision likely to affect things relative to that one, given the current uncertainty about where we're at in terms of the current state. Okay? Any questions about this? Yeah.
Question?
Yeah.
Just wondering, for some problems like this where you're just fitting it really to one kind of data point, the likelihood function might be reasonably simple.
Yeah.
How difficult does it get to specify that?
If you have many data points, or many types of data.
Yeah, for example.
Yeah, we've done significant work with that, and we've had some pretty good success. I mean, I have to say that the strategy we've used has been fairly straightforward. I think it's a fairly common strategy, but basically we've multiplied the likelihood with respect to one by the likelihood with respect to the other, for example, and still gotten some pretty decent results. So what gets harder is if you start needing to derive a multi-dimensional likelihood function based on first principles. That's harder, but we've had quite some good luck taking into account multiple lines of evidence in terms of that likelihood, and it seems to work pretty well. We're doing a couple of types of work right now with this, which are exploring that issue. I mean, one of them is we're using this with the diabetes model, where we have for every time point something like 168 different types of observation. So an observation for each, excuse me, not 168. It's 84 types of observation for every time point. over 25 years. So we have it basically for each ethnic, age, and gender group. We have some data coming in, and we're trying to adjust the model's expectations, particularly around latent number of people with prediabetes, the number of people I'd expect to have prediabetes or undiagnosed diabetes. And there, we're really dealing with this issue of lots of types of data we're dealing with at once. I'm not too afraid of it based on the success we've seen in other areas where we have several types of data, but that's going to be a real test because we're going to have very long likelihood function. I will tell you that another related point is the technique is pretty effective even when you have missing data that's missing. You have these data points successfully. Maybe you have two types of time series over time. Sometimes one is missing data, sometimes the other, or maybe one is updated at irregular intervals compared to the other. We've been able to use it quite well in that context too. Good question. Other questions? Yes?
I've got a question that may be completely mad. It's fascinating. I'm just wondering, in the range of interactions of different fields that we talked about, has there been any commentary on this from quantum physicists? Because although it's just allegorical, some of what you're describing sounds very much like the way that some quantum physicists write about their interpretation of quantum physics in terms of the Everett many worlds interpretation.
Oh yeah.
Which has this idea of, so you've got constantly diverging universes.
Yeah.
So this may, which would open up the possibility that this may not just be a way of modelling the one universe, but this may actually be something that's quite close to how the universe actually works.
Oh,
which is to say that it's constantly going off in myriad different directions, and then we're just steering away from one of them.
Yeah, that's intriguing. No, I think that's fascinating.
Okay.
One of my students who's working on this, Kirk Kruger, is from a physics background, and he has some interest on the sort of quantum mechanical side. I had another student who also worked on this, also with a PhD in physics, who I didn't though talk with him about that. I'd be interested in doing that. It might lend some insights into, because one of the prerequisites that I mentioned for applying this approach is actually this approach doesn't make sense unless your model has stochastics in it. Why? Because well, you can imagine if you have only one particle, if it's totally deterministic, that particle is never gonna change. You're not gonna have a distribution of particles. You're gonna have a single particle. Thinking this is the situation. It's only if you get divergence, in terms of sort of different particle hypotheses, as it were, and if that it benefits. And more than that, when you resample, one really highly weighted particle might become 100. Represent 100 out of the total of 10,000. And then those particles, to not become degenerate, like where they all have the same, again, more and more confidence this is the truth, they've got to diverge. And for it to be healthy, there should be ongoing exploration on their part about what's really the case, and that requires stochastics. And possibly I could easily imagine from a physics standpoint, getting some helpful guidance on what forms of stochastics might be the most applicable one to incorporate into the model. Like where should that stochastics lie within the model? When we have Kalman filtering, we have stochastics assumed of certain sorts, and it's a more uniform thing. For this, I often find myself saying, okay, we'll assume the stochastics on this parameter, again, like the fraction of people that are reported. I think, okay, during an outbreak, that seems quite likely to change. And it's a little bit ad hoc for my taste, and I think maybe a quantum physicist would be able to give some suggestions about how I might, in a more principled way, accommodate more thoroughgoing stochastics, not so much concentrated all at just one or two or three places, but more throughout the model.
Yes.
So that could actually be a very fruitful discussion, and
I do know some people who, do quantum field theory and so on, and maybe I could tap some of their thinking. So I'm grateful for the suggestion. Great idea. And in general, I find it very appealing, this notion, as a skeptical modeler, that, a model could have many theories about what's going on, rather than putting all our emphasis into, this is the single most consistent theory. Let's put all our eggs in that basket. Yeah. Other questions? Alas, I've striven hard to have a good representation in topics in this boot camp, and to adjust my level of detail for different topics based on the interests and where we're at. But I think even for me, trying to cover in 3 minutes intervention, representation of interventions will be challenging. What I will do instead is point you to another boot camp where we've captured interventions in a way that's very, very powerful, which allows each scenario to specify within it a different intervention's rule or strategy. So this scenario can say, when we intervene upon someone, we will do so by changing their likelihood of initiating smoking in a certain way. Another one will focus on cessation. And orthogonal to that, sort of at right angles to that, independent of that, I have another rule on who do we focus it. Is it people in this and the youngest age categories who are uptaking smoking? Is it women in childbearing years? Is it individuals who have been heavy smokers for many years? Allowing us to separately specify each of those without hard coding it into the model, just in experiments, in the scenarios, allow us to specify those things and then run the model with that appropriate scenario. I will point you to a video that explicates this some, and I'd be glad to explain that further. Also, I know there was interest in Winchell's R tool. I know from Amir here, and Winchell has suggested that he'd be glad to directly show that. So if you want to seek him out, he's in yonder. Yeah, he's loitering outside the loo, but without intent. So he's actually working on a very important modeling project there, but I would invite you to talk with him and see it. If anyone else is interested, we can Winchell do a show and tell. If anyone is interested in seeing particle filter models, I can also upload a few of them to the site. And I've evolved, since we've done maybe 7 of them now, something like that, we've evolved kind of a recipe for creating them that takes stock features that have been in earlier ones, copies those into a new one. Those are just used directly, and then you have to modify these certain places in your model. It's kind of a recipe, a cookbook for creating them that gets you most of the way, and then you have to experiment with them some to tune the parameters. And if people are interested in that, there's some videos I've recorded as well with that, but I'd be glad to share the example models. Okay, and you can actually run them and see these sort of patterns play out over time and so on. Okay. Ladies and gentlemen, it has been my profound honor, privilege to be with you this week. I'm just so grateful for your attention, for your stamina, and for your consistency of efforts and excellent questions. This has been an extraordinary group. As I said earlier, we've gone deeper than we have in any other modeling bootcamp I can remember in terms of the sophistication of the models. And the credit is wholly yours. So thank you very much. I know this is, there's much that couldn't be covered. You will find many resources online, and we'll work to make sure that those resources I have pointed you to, the boot camps, the online health modeling community site, we'll work to make sure that those work to address. If you're interested in learning more, that we'll work with you to try to address those. We'll have some curation, and we'll remove the FIFA postings from that site. Yeah. So thank you, everyone, so much. Safe travels back home. Thanks for all your attention, and I'll look forward to seeing you in future trips down under. Thanks.
Thank you so much. Too kind.